So one of the more accurate method of assessing mitral regurgitation is the so-called PISA method, and it stands for proximal isovelocity surface area. And as we showed you the picture, let's see if we can find that picture. But when you have regurgitation, when you have a backflow of blood from the left ventricle across the mitral valve and into the left atrium, so the regurgitation is going backwards. Forward, you're going to have what we call flow convergence. And the flow convergence is actually a series of hemispheric shells. Okay? On the surface of these hemispheres, the velocity is the same. So that's why we call it isovelocity surface, and it's on the surface. So proximal isovelocity surface area. And let me just find. So again, in any regurgitation scenario, you're going to get your proximal isovelocity surface area. And so it's important to get that concept straight. Okay. All right. So this sort of depicts it fairly well. So again, when you have, say, mitral regurgitation, this is the LV, left atrium is right there. You have the blood is regurgitating backwards, it's going backwards from the LV into left atrium. You're going to get a series of hemispheric shells on the opposite side of the valve. Okay, series of hemispheric shells. And as we mentioned before, the narrowest portion where so the regurgitation is going this way, the narrowest portion is what we call the vena contracta. The area through which the regurgitation is occurring is what we call the EROA, effective regurgitant orifice area. So these hemispheric shells, okay, so it's like half of a sphere. So on the surface of these hemispheres, the velocity is the same. That is why we call it uh, iso velocity. And if you take it from the base, so from the base to the surface of the shell, this is what we call this is the radius. Because remember, this is a hemisphere. So if you could draw it, okay. So remember, a hemisphere is just a half of a sphere. So this, so if you could draw it like that, so this would be half of the sphere, and so say the base of the sphere is right there. Okay, so this is the radius. This would be the radius. Okay, so when we talk about the radius, it is from the surface of the shell to the base. Okay, and then all the velocity on the surface. This is the surface area. All this velocity is going to be the same. Every point, all the points on this surface is going to have the same velocity. The good thing about when you're doing PISA, you can adjust your this is what we call the Adelson velocity. and you can adjust your aerosin velocity. We call it a baseline shift. So you can adjust the aerosin velocity to get a nice hemisphere. Okay, so you can adjust the aerosin velocity to get a nice hemisphere. So even if you start out by not getting a nice hemisphere, once you do your baseline shift, you can get a nice hemisphere. Okay, and again, this would be the radius. So radius r, and this velocity, the velocity in this surface is actually the aerosin velocity. If you look closely here, you see a velocity which is, I think, minus 45.2 centimeters per second. So that is the velocity on the surface right here. Okay, and then all of this down here is the regurgitation. If you remember your conservation of mass, using the continuity equation, the flow, the regurgitant flow, which is right here. So all of this is the regurgitant flow. The regurgitant flow is the same as the flow at pizza, okay, using the conservation of mass principle. So the regurgitant flow, so the blood going backwards, the flow of blood going backwards into the left atrium is equal to the flow at pizza, same flow, because of the conservation of mass. If you remember, when we say flow, flow is equal to cross-sectional area times velocity, right? So remember, we established that. So remember from your hemodynamic principles, flow is equal to cross-sectional area times velocity. So the regurgitant flow is equal, so let's just do the regurgitant flow, which is equal to the flow at pizza. The regurgitant flow, let's just do the regurgitant flow. The regurgitant flow is equal to the cross-sectional area. And the cross-sectional area that we're talking about is the area through which the regurgitation is occurring. It is EROA, EROA, effective regurgitant orifice area. This EROA is a dynamic area. It's not a fixed area, because if the regurgitation increase, the EROA is going to increase. If the regurgitation decrease, the EROA is going to decrease. So it is the area at or close to the vena contracta, the area through which you get this regurgitation going through. So the regurgitant flow is equal to the EROA A, okay, times this regurgitation velocity. Now you just stick your CW there and you can get the peak MR velocity. So the peak MR velocity is the velocity that we're talking about. So it would be VMR. So the peak MR velocity. Okay. So the regurgitant flow, that is the flow of blood going backwards, is equal to the area, which is EROA, times the mitral regurgitation peak velocity. Okay? And we say that this regurgitant flow is going to equal to the flow at pizza. The flow at pizza. So the flow at pizza is All right, so the pizza flow so flow is always equal to area times velocity. Remember what we said that this area, you're going to get a series of hemispheric shells. Hemispheric shells. The area of this hemisphere is 2 pi r squared. 2 pi r squared. That's the area of a hemisphere. The area of a sphere is 4 pi r squared. So the area of a hemisphere is 2 pi r squared. So flow at pizza is equal to the area, which is this is a hemisphere, times velocity. And the velocity that we're talking about is the velocity on the surface. Okay? And that's the Arison velocity. So remember, the reason why we call it pizza is because it's proximal iso means the same, velocity surface area. So all along the surface, the velocity is the same. And this velocity on the surface is the Arison velocity. So we call that VA, Arison velocity. Okay? Now, remember, you're going to set the Arison velocity, you know that. When you adjust your Arison velocity to get your nice hemisphere, you can measure radius. So you know that. So you know everything right here. Pi is a fixed number, 3.14. And then you adjust the Arison velocity to get your nice hemisphere and hence the radius, which you measure. So you plug it in there, you have your Arison velocity. The only thing you don't know is the EROA, because when you do your C doubler for the mitral regurg, you can measure the peak mitral regurgitation velocity. The only thing you don't know is the EROA. So once you put your equation together, you can solve for the EROA. We can use the EROA to determine the severity of the mitral regurgitation. The larger the EROA, the more severe the mitral regurgitation. The less the EROA, the less severe the mitral regurgitation. All right, so that is the concept of PISA. That is the concept, okay? All right, so let's move on. All right, so this is saying the same thing. So the regurgitant flow is equal to this, and this is the flow at PISA. Just rearranging the equation, you can solve for EROA. And again, you can determine the severity of the regurgitation by looking at the EROA. If the EROA is a large number, then you have a large regurgitation. If the EROA is a small number, then you have a small regurgitation. Okay, so again, this is a cartoon showing the same thing. If you adjust the Arison velocity, you get these nice hemispheric shells. Okay, it's not it's half of a sphere, and you can measure the radius. Okay, this is the regurgitation right there. The regurgitant flow is equal to the flow at pizza. So this is an actual case. So this is the flow convergence with your hemispheric shell. Just adjust a baseline shift of your velocity. and you get a nice hemisphere, and you just measure the radius, just the radius. Okay, so this is actually a somewhat eccentric MR jet, but you still get your nice flow convergence. This is the Adelson velocity. Okay, so the only unknown when you put everything together is the EROA. The only unknown is the EROA. So this is the formula we get for EROA: 2 pi r squared times the Adelson velocity over the velocity of the mitral regurgitation. You can measure the mitral regurgitation velocity. The Adelson velocity is right there. You measure the radius, so you can solve for EROA. What you can do is you can adjust your VA, Adelson velocity, to 40 centimeters per second. If you adjust your Adelson velocity to 40 centimeters per second, and you plug everything in the equation, you'll find that the EROA is equal to R squared over 2. So what they'll do in the exam, they'll give you an elaborate thing. They're going to tell you that, well, they'll show you, or you can see that the Adelson velocity is 40 centimeters per second. And you'll also see that the mitral regurgitant velocity is 5 meters per second. So if the Adelson velocity is 40 centimeters per second, and the mitral peak velocity is 5 meters per second, then EROA, once you plug it in the equation, EROA is now R squared over 2. So what they're going to do is they will tell you that, or you can see it, they'll show it to you. It will be on some diagram or some image. VA will be 40, MR will be 5 meters, and then they will show you the radius. And all you have to do is square the radius, divide it by 2, and you get the ROA. They probably don't give you the figures like how I give it to you here, but they'll give you a Doppler, and if you look closely, you'll see that the mitral regurgitation velocity is 5 meters per second, and then they'll give you the color bar with the Adelson velocity, and it will be 40 centimeters per second. So once you know that if these two things are met, then you know that EROA is R squared over 2. So they'll give you'll see where R, you can, on the hemispheric flow convergence, you will see R. And to get the EROA, you just square R and divide it by 2. Also, if the Adelson velocity is 30 centimeters per second, and of course you can see, they don't have to tell you that. Once you look at the right hand side, you'll see the color bar, and the Adelson velocity will be there. And if the mitral regurgitant velocity is 5 meters per second, if R is greater than 1, then the MR is severe. Okay? If R is greater than 1, then the MR is severe. So these are little things that you have to know. Okay? All right. So if you were doing PISA, your Vmax, the mitral regurgitation velocity, you just measure it there. In this case, it will be 4.85 meters per second, or 485 centimeters per second. And then this will be your Adelson velocity. Okay? The Adelson velocity will be 56. Okay? Now, after you calculate your EROA, so you have to calculate the EROA using the principle we just went over. Okay? So you have to use this to calculate your EROA. After you calculate the EROA, then you can calculate your regurgitant volume. The regurgitant volume is the EROA times the TVI. So you get your MR envelope and you have to trace the border to get the TVI. So if you multiply the EROA times TVI, you get regurgitant volume. Remember, a large amount of regurgitant volume tells you that the MR is severe. And we're going to go over the table looking at mild and severe MR. We went over this in hemodynamics. We're going to go over it again. Okay. So to get the regurgitant volume, it's the EROA times TVI. Okay. To get the flow, it is EROA times the velocity. So again, to get the TVI, you have to do planimetry of the Doppler envelope. To get the regurgitant fraction now, it is the regurgitant volume over the mitral inflow, because we're talking about with regurgitation, you're going to get the blood going back into the left atrium, and then in diastole, the regurgitant volume plus the regular volume is going to go through the mitral valve. So the mitral flow or the mitral inflow is going to be a combination of the normal flow plus the regurgitant volume. And again, flow is the area, the definition for flow is always going to be the same wherever you are. So mitral inflow is the area, this is the mitral valve area times the TVI. The mitral inflow volume is going to be the area times the TVI. So again, you'd have to look at get the diameter. You're going to get the diameter of the mitral annulus. Okay, so to get the mitral valve TVI, you look at the mitral inflow and you just trace the spectral envelope. Okay, you get the TVI. And for the mitral valve area, okay, we have to assume that it's circular. And the area of a circle is pi r squared, and r is the radius of the mitral annulus. Okay, all right. So if you so again, the mitral inflow. This is the regurgitant fraction. So we showed you how to get the regurgitant volume. Regurgitant volume is equal to the EROA times the TVI, regurgitant volume. The mitral inflow is equal to the mitral area times the TVI of the mitral inflow. Okay, so once you do that, you get that, you rearrange your equation, you get that. So, all right, so